So how many of you remember partial fractions from pre-calculus? And I don't know if you had me or if you didn't have me, but I waved my hands and I stomped my feet and I screamed and yelled and I said, you gotta know these because they'll make your life easier when you start messing with the calculus. I gotta change out of this puke green. Let's go to just regular old black. All right, what if I want to take the integral of, say, I don't know, let's go dx over x squared minus 3x minus 10. Okay, that guy. Now again, think of your tools that you have. Now this is where it gets hard. This is where integrating, the more tools you have, believe it or not, the harder it gets, especially as journeyman integrators, because you don't know which tool to grab. It's like, well, can I do a U substitution? Well, what are you going to let U be? You're going to let U be the denominator? I don't see a 2x minus 3 in the numerator. That's not going to help. Is it one of my fantastic, I forget how many there are, 15 or whatever, that I've memorized? I've never seen this before. It looks a lot like, I don't know, maybe an arctan or I don't know, something like that. The problem is, can I do it by parts? Sorry, I have to interrupt myself. Can I do it by parts? Well, maybe, but again, what am I going to let my U and my dv be? So that's where it gets really, really tricky. Well, this is one of those problems where it actually gets quite fun. Now, hopefully, if you remember your partial fractions, what we're going to do is we're going to look at 1 over x squared minus 3x minus 10. Now, what tells me that I might want to use partial fractions? Well, A, all my other tools don't appear to be working very well. And B, this denominator factors. So I can look at this as 1 over x minus 5 times x plus 2, right? Remember how this worked? I can take 1 over x minus 5 times x plus 2. Now I'm going to walk you through both ways because it may have been a while since you did this. All right, and this becomes a over x minus 5 plus b over x plus 2, right? So I know, remember, if I find a common denominator, I get 1 over x minus 5 times x plus 2 equals a times x plus 2 plus b times x minus 5. All I did was find a common denominator. And then once I have that common denominator, I can disregard it. Because really, I'm just trying to solve for a and b. Now, let's see if you remember this trick. Let x equal negative 2. If x equals negative 2, the left side goes unscathed, so I get 1 equals, well, this term goes to 0, so this becomes 0 plus b times negative 7, right? Which implies that b equals negative 1/7. How about if I let x equal 5? Remember that? Well, again, the left side goes unscathed, so 1 equals, now I get a times 7 plus b times 0, right, which is just 0. So a equals 1/7. Now, what does this imply? I'm going to draw myself a little line right here. This implies that 1 over x squared minus 3x minus 10 can be written as what? 1/7 over x minus 5. Now, b is negative, right? So it's minus 1/7 over x plus 2. Now, if I don't believe myself, I can cross multiply and see what happens, right? If I cross multiply, I better get a 1. So I would get 1/7 x plus 2/7, right? Minus 1/7 x plus 5/7. Last time I checked, 2/7 plus 5/7 is 7/7, which is 1. That's fabulous. So what's that tell me? That means I can rewrite this as the integral of 1/7 over x minus 5 minus 1/7 over x plus 2 dx. Or let's just get that thing out of there and go 1/7 times 1 over x minus 5 minus 1 over x plus 2. Now, if you're one of these students that looks at this and for whatever reason you want to combine the terms and do what you were doing before, you wouldn't be the first. But remember, we broke this thing up into partial fractions so that we could deal with these fractions individually. Now, hopefully you've done enough mathematics to realize that for this guy, the integral of a sum is the sum of the integral, so I can deal with these guys separately. If I let u equal x minus 5, then du equals dx. And guess what? I've got an integral of 1 over u, which is the natural log of the absolute value of u. Okay? Same thing goes here. The exact same technique, not the same numbers, but the same technique. So what happens? Watch. And again, I work quickly with these. I expect you guys to play with these a lot. However, I want you also to be able to do integration by substitution relatively quickly. I want you to practice with that. So this guy is going to end up being the natural log of the absolute value of x minus 5. Again, you could just do this simple, use substitution if you don't believe me, minus the natural log of the absolute value of x plus 2. And then, of course, let's not forget our plus c. Now, I'm going to show you something that drives calculus students nuts. They do all this fabulous work. Things get it's just awesome, right? I am so good at this, especially on like a multiple choice test. All of a sudden, they look at this solution and they don't see their answer. Wait, what? Why don't I see my answer? I worked really hard. I did what Ripley told me to do. What the heck's going on? Ripley must hate me. No, I don't hate you. You just got to remember your algebra 2. Remember your laws of logarithms? This can be written as 1/7 times. Remember the difference in natural logarithms is the natural log of a quotient. So I can actually rewrite this as the natural log of the absolute value of x minus 5 over x plus 2. I don't know where I wrote double pluses right there. I told you you were going to need this again. Plus c. And furthermore, remember the rule about coefficients of logarithms? They become exponents. So you could actually see this as the 7th root of the natural log of, excuse me, let's try that again. Wait, Ripley's acting crazy. This becomes the natural log, I got ahead of myself, of the 7th root of x minus 5 over x plus 2. Now you may ask me, of course, absolute values, you may ask me, wait a sec, Ripley, do I have to do this every time? Well, no, but sometimes you may have to match up a solution that you've done with, say, a multiple choice solution. Or I may say prove that something else equals something else. So you're going to have to remember these laws of logarithms that you thought that you could forget after Algebra 2. Ha ha, told you so. All right, I'm just making fun because I'm mean and angry. All right, so enjoy. We're going to play with these. Oh, wait, there were a couple of crazy little rules that I did want to talk to you about. Let's try this guy, just for giggles. Let's do the integral of x over x squared times x plus 1. We'll keep it simple. Here, the x. Now, what's the first thing you might want to do? Well, you might want to do a u substitution here, right? If I go u equals x squared, and du equals 2x. Ooh, cool, that's wait, I have to account for this? If I have to account for x plus 1 and I solve for x here, then I'm going to have a du in the denominator. I am dividing by the width of the subinterval. I'm dividing by the width of a rectangle. That's not going to work. Okay, so, well, we're not afraid. Don't panic, because we just did a little partial fractions. Again, the caveat here is I just handed you a tool. At the end of the chapter, when we have a test using all these tools, you're going to have to be able to figure out which tool to pull out of the bag and when. So let's do a little bit of algebra here. X over x squared times x plus 1 is equal to, now you ready? Remember how this works? It's going to be a over, now, how does this work with this x squared? Do you remember this? If I've got a factor that's squared, remember how it worked? Because I'm not going to write ax plus b because that actually makes it harder than it needs to be. I'm going to write a over x plus b over x squared. Remember how that, if I had those repeated factors, this, I only do this because I've got an x squared. If this were x plus 1 squared, then I would go plus c over x plus 1 plus d over x plus 1 squared. But I don't, so I'm not going to make it more complicated than I have to. Okay, when you've got a repeated factor, in other words, I've got an x squared, then I got to do an x and then an x squared. Hopefully you remember that, but perhaps you don't. I wouldn't blame you if you didn't. So I got x over x squared times x plus 1 is equal to, now find a common denominator. We have the denominator sitting right there. So I got to take a and I have to multiply it times an x and an x plus 1 to get to the common denominator, don't I? I have a b, it's got an x squared under it, but I need an x squared times x plus 1, so I have to multiply it times x plus 1 to get to the common denominator. Simple fractions. It's done with ugly symbols, but it's still just simple fractions. And then I just go plus cx squared, and this whole thing ends up over x squared times x plus 1. All right, now let's see what happens. what happens if I like all these individual x's sitting here. I'm going to let x equal 0. If x equals 0, then I get 0 equals, now notice if I plug 0 in here, I get a times 0 times 1, which is 0, plus b times 0 plus 1 plus c times 0. So I end up with 0 equals, that's gone, 0 equals b. Hey, that's a good piece of information. That's really nice, isn't it? All right, what else could I get rid of? Well, how about let x equal -1? If I let x equal -1, then this guy goes away and this guy goes away, and I end up with -1 equals c times -1 squared, which is just c. Hey, look, I got c. All right, so the question is, I know what b is, I know what c is, right? So how am I going to be able to solve for a? Do you remember? Let's see if you can remember from pre-calculus. How do I do that? Well, think about this. I know that x equals a times x plus 1. I know that b is 0, so I'm not even going to include it. And then I know that this is going to be plus c, right? Right? Or excuse me, minus 1. What am I doing? Plus c. I know that c is minus 1. So the easy way to solve for c is simple, or excuse me, slow down, Ripley. Sorry, the bell just rang, so I'm trying to hurry. Is just grab some other value. How about letting x equal 1? I like 1. It's a nice number. 1 equals a times 1 times 2 minus 1, right? Add the 1 across. I get 2 equals 2a, so a equals 1. Isn't that pretty? Which implies that what? Well, I can rewrite this integral as, I need to steal this corner because there's no way I'm going to remember that. I can rewrite that integral as the integral of a, which is 1 over x. B was 0, thank God, right? Plus c, which was -1 over x plus 1, right? Now, I got a question, and probably most of you caught this, but I just kind of threw it out there just for fun. Do you notice what happened here? It's so cool because the algebra takes care of itself. Notice here, if I wanted to, you may have been waving your hands early going, Ripley, why didn't you cancel the x's? 1 second, okay? Why didn't you cancel the x's? Well, let's say that I forgot to cancel the x's. Right? This x and this x could have canceled. However, notice that the algebra doing partial fractions took care of it for me, which makes it lovely. Now, I punished myself by not canceling the x's because I had to deal with this ugly part right here. But when b equaled 0, it took care of itself for me. Isn't that fantastic? Now, this is a relatively integral to do. See if you can do it real quick, and we'll talk about it in class if you have further questions. All right? Thanks for your time and attention, and I'll see you in class tomorrow.